Now in this lecture, we shall be discussing about a dynamic response factor and how we can calculate that as per the AS1170.2 2021. So when we are dealing with the dynamic response factor, it is not that we have to calculate a dynamic response for all kind of structures. We have to calculate the along and across wind response of structures which are only dynamically responsive or dynamically active. So this standard, we can say that it is not that it provides the dynamic response factor for all kind of structures. There are some exceptions also. First exception is that first mode natural frequency less than 0.2 hertz. It means that the time period of the structure, if it is greater than 5 seconds, only then we can say that the frequency is less than 0.2 hertz, and that is a very tall building, we can say. Height greater than 200 meters, or wherever significant coupling is evident in first three modes of vibration. Coupling means that when we do the dynamic analysis, we do get the response, and when because of the irregular structural geometry or because of the irregular structural configuration, it may happen that the building becomes responsive primarily in the coupling itself. That is the X mode translation and Y mode translation, we can say, happen simultaneously. So that is an exception, and how we can treat that is that we can revise the structural configuration, and on the basis of that we can avoid the significant coupling in the first three modes of vibration. Usually first mode is linear and the translation happens along the x-axis. Second mode is also linear and the translation happens along the y-axis, and the third mode is a torsion. So the building deforms about the, we can say, center of the rigidity. After that, buildings and structures that have two fundamental mode of sway within 10% of each other and both are less than 0.4 hertz. So when we're talking about the buildings that have two fundamental modes of sway within 10%, so what happens is that, let us say, when the building is getting translated in the x, the time period that we are getting is approximately, let us say, 1.4 second. And when the building is translating along the y, if that is the second mode of vibration, we are getting time period of 1.35 second. So we can say that if we are getting the time period for first mode as 1.4, time period for second mode as 1.35, in that particular case we do get the the two fundamental modes of wave within 10% of each other, and in that particular case it is not recommended that we have to do we can follow formulae given in the code. So after that, buildings with a height to, we can say, minimum overall width ratio of greater than 6. Fourth point is that linked or connected building where the connection extends above h by 5 and the first mode natural frequency is less than 0.5 hertz. Another case is that cases that involve excitation resulting from aerodynamic interference from other structures. Roofs supported on two or more sides with natural frequency less than 0.8 hertz. Cantilevered roof with first mode natural frequency of less than 0.5 hertz. So if this is the case, and then we can say that the time period or the span of the cantilever is huge. And facade elements such as sunshades. Now, what if we are having a structure in this particular case, and we have to design the structure. Now for this case where there is this coupling of the fundamental modes, or we can say that because if we can change the structural configuration to have a correct dynamic response, for that we can correct that. But what if the span of the cantilever roof is huge, or the span is like in the range of 25 meters or 35 meters? So for that, we do have an option that we can do the wind tunnel testing. So wherever we have a doubt, or wherever we have to do the optimization also, it is always recommended to opt for the wind tunnel testing. So after that, in which kind of structures we can take Cdyn as 1. So dynamic response shall be taken as equal to 1 for the following cases, that is building and freestanding tower where the natural frequency of first mode of vibration is greater than 1 hertz. So even if the natural frequency is 1.01 hertz of a, we can say, building or for a freestanding tower, then also there is no need to do the dynamic analysis. We can just simply take Cdyn as 1. Poles and chimneys with height to average diameter aspect less than 5. What it means is that, let us say we are having a chimney here, and the dia of this chimney is, let us say, 500 mm. and the height of the chimney is only, let us say, 2000 mm, and I can say that that does not exist. So it is just a preventive methodology that the code has adopted. So usually for 500 mm dia chimney, we are talking about a height which is approximately 30 meters to, we can say, 50 meters also. So obviously for that particular case, the aspect ratio becomes huge. And after that, the ground mounted solar panels with natural frequency greater than 5 hertz. Now this is somewhat little challenging because it is very difficult to predict the ground mounted solar panels natural frequency, especially when we are dealing with we can say uh, arrays of solar panels. So after that, the other structures, the following requirements shall apply. So for buildings and freestanding towers, so basically the thing is that in the code there are 4 different types of calculations that are given to help us calculate the Cdyn for different kinds of dynamically sensitive structures. First case is that for buildings in freestanding tower, where the natural frequency is in the range of 0.2 to 1 hertz, and Cdyn shall be as per this clause 6.2 for along and clause 6.3 for the crosswind response. So we shall discuss in detail about the crosswind response in a separate lecture. In this particular lecture, I am focusing on the along wind response and Cdyn values. For cantilevered roof with first mode natural frequency between 0.5 and 1 hertz, Cdyn shall be as per this. For dynamic response of poles, mast and chimneys of circular cross section with height to average diameter aspect ratio greater than 5 shall be determined from this and this. The dynamic response factor for horizontal cylinder structures with the first mode natural frequency between 1 and 0.5 hertz, Cdyn shall be as defined in clause 6.2.3. Now, we shall discuss or we shall calculate all of these values. So I have prepared an Excel file which shall help you in understanding all the formulas that are given to calculate the Cdyn for tall buildings and towers, for tower, poles and mast. Let us say if we're talking about this kind of mast structures which are usually installed in the cricket stadiums or in the other stadiums also. So for the lighting, so that is the another, and after that we can calculate the Cdyn for the horizontal slender structures also. So we shall calculate that, but just to give you a theoretical introduction here, we shall start calculating the Cdyn for along wind response for different kind of structures. Second concept is that whenever you feel doubt that the structure that you are handling or designing is beyond the scope of this particular code, we can always go for the wind tunnel testing. So that should be considered for tall buildings when the crosswind response exceeds the along wind response determined from the same axis direction. So even if you have a structure where you are having these kind of behavior, or you come to know that we can say a crosswind response is exceeding the long wind response. So for that also you do need to prefer to the wind tunnel testing only. So special studies such as wind tunnel testing should be undertaken for dynamically sensitive structures which are not covered by this standard. So this code is also helping us calculate the acceleration for serviceability in tall wind sensitive structures. So that we have studied in the earlier lecture that how the acceleration plays a very important role in the comfort level of the persons that are in a particular building at a time of the extreme winds. So for structures with high frequency, designers should also consider the possibility fatigue failure. So after that, this is the first scenario where we shall be calculating the Cdyn for simple tall buildings and freestanding tower. But you need to understand that right now we are only talking about the along wind response. So I shall just give you a brief preview before I start discussing this, and we shall also solve a practical example of how we can calculate the Cdyn values. Now the first thing that you need to understand is that, let us say you have a tall building which is having, let us say, 40 number of floors, and you do need to design the particular, we can say, building. Now if we need to design this particular building, we do need to understand that the value of the Cdyn at this height, let us say x, and the value of Cdyn and let us say this height, let us say it is x1, or the value of the Cdyn and let us say the top, let us say assume it is x2. So the value of Cdyn shall not be same for all of these we can say different heights. It shall be different. So first thing that you need to understand is that the code gives us two variables. This x2 is named as, we can say, h, and this x1 or x, that is named as s. So one of the question, the first question that comes in the mind is that what exactly is meant by the s. S is the level at which the action effects, that is the value of the Cdyn, is being calculated. And if we have 40 number of floors, we have to calculate the 40 number of values of Cdyn, because the value of the Cdyn shall be different as soon as the S becomes different. So for 40 number of floors, we have to calculate different values of the Cdyn also. That is 40 different values of Cdyn shall be calculated. So after that, the second concept that you do need to understand is that for the calculation of action effects, what exactly are the action effect? It is the bending moment, shear force, and the member forces at a height S. So according to the height S, all of these values also changes. That is the bending moment, shear force, and the member forces. So this factor, that is the value of the Cdyn, is dependent on both Z and S. And after that, for calculation of base bending moment, deflections, and acceleration at the top of the structure, a single value of Cdyn shall be used with S taken as 0. So we can very well understand that, if we are talking about the, we can say if we want to draw the bending moment diagram, assuming it as a free, cantilever, this shall be the cantilevered bending moment diagram with, we can say, maximum value of the bending moment at the base. If the maximum value of the bending moment, or we can say shear force also, is at the base, then S is equal to 0 in that particular case. So by taking the S is equal to 0, we shall be having the calculation of the, we can say, base bending moment, deflection at the top, and acceleration at the top of the structure. I'm repeating here, by considering S is equal to 0, we shall be getting the base bending moment, or the bending moment at the, we can say, foundation level, and we shall be getting the deflection and acceleration at top of structure. So that is also an important concept that you do need to understand before we proceed further, and that is also a very confusion that I have seen among the structural engineers. That first confusion is that what exactly is meant by the S, that you have understand that the level at which the action effects needs to be calculated. The second confusion is that what if we want to calculate the extreme values, that is we want to have the, we can say, the maximum values of the base bending moment. We have to calculate the acceleration at the top. We have to calculate deflection at the top. For that, the value of S has to be taken as 0, because we have to consider that at the base level. So after that, the dynamic response factor. So that dynamic response factor Cdyn shall be calculated with this particular equation. Now, if you are seeing this for the first time, this equation might be a little bit confusing, or we can say difficult to calculate, but let me assure you that it is a very easy equation, and we can say that more or less it is derived from the Davenport research studies only, and in line with the ISO. So if you are calculating the gust factor G as per ASCE, or if you are calculating the values as per the EC0, that is the European standards, or if we are calculating the values of the, we can say, the gust response factor as per the Indian standard AS1170, more or less the equations that, or the terms, or the definition that are being used are same. They are not that much different. Like in American standard, the difference is coming because of the difference in units. But all of these countries do talk about all of these terms. One term they talk about is the turbulence intensity. Second term they talk about is the peak factor, GV. Third term, all of them talk about is the background factor. So background factor is basically the measure of slowly varying background component of the fluctuating response caused by low frequency wind speed variation given by this particular equation. So background factor has to be calculated. Doesn't matter in which country you are doing the structural engineering. After that, LH is a measure of integral turbulence length scale. So this also equation is also like, used all across the world. 85 s to the power 10 divide to the power 0.25. After that, peak factor for resonant response for 10-minute period is given by this equation. So this equation is also used in the other standards. After that, size reduction factor S. Now this equation, although other countries code are also using the size reduction factor, but this equation is a little bit different when we compare to the other country codes. So in here, there are these values: 3.5 NAH, V design theta is the design wind speed. We're talking about the B0H, we're talking about the GV and IH. So I won't be diving deep into it, but we shall be calculating the practical example which shall help you in understanding all of this very quickly. ET is the spectrum of turbulence in the approaching wind stream given by this particular equation, and NA is the first mode natural frequency, and V design theta is the building design wind speed. This is basically the ratio of the structural damping to the critical damping of the structure. Now this value is given as 0.015 to 0.02 for steel structures, and for reinforced concrete it is 0.02 to 0.303. So concrete has, we can say, higher damping capacity as compared to the steel structures. Now these values of the damping are for the ultimate limit state only, because in the ultimate limit state the section do get cracked and we do have much more dissipation of energies. But when we're talking about the serviceability limit state for deflections, the values should be different. And if we are talking about the serviceability limit state for annual peak acceleration, the value shall be 0.005 to 0.1 of critical, and for reinforced concrete it is 0.008 to 0.012. So for deflection, here you can see that the values of the damping that has to be taken as 0.01 to 0.012, and for reinforced concrete it is 0.01 to 0.015. So in simple terms, we can say that if you're talking about the ultimate limit state, the damping values are the maximum. 0.02 for, we can say, steel, and 0.03 for reinforced concrete. For steel structures, for serviceability limit state, that is to calculate deflection, it is 0.012 in contrast to the 0.02 for the ultimate limit state, and this again reduces to 0.01 if you're talking about the acceleration. So 0.03 for ultimate and 0.015 for the, we can say, deflection, and 0.012 for the acceleration, we can say, calculation for the serviceability limit state. Now, we do need to understand that above ranges are intended to accommodate various tip deflection to height ratios. So if required, user is free to seek other sources for advice on possible values of structural damping. But as per my experience, these values are correct values. We can trust the the code, and we can go ahead with the damping values that are given in the code here. Now we shall be calculating the first example, that is value of the Cdyn for tall buildings and towers. So let us assume the design wind speed. We do know how to calculate the design wind speed, that is V design theta. We have already calculated many times, so I'm not repeating that calculation here again. So assuming the value of the V design theta here is 60 meter per second, first mode natural frequency of vibration in the along wind direction, that we can assume it as 0.7 hertz. After the height of the level at which action effects are calculated, we can assume it as, let us say, 50 meters. And height to the top of the structure, that is H, that we can assume it as 100 meters. After that, the first values that we do need to calculate is the turbulence intensity. Now turbulence intensity is basically a function of two parameters here. One parameter is the height of the structure, second parameter is the terrain category. So as we go to the we can say higher terrain categories, that we are expecting much more disturbance, the turbulence intensity value increases. And as we go up, here we can see that turbulence intensity value decreases, and here also we can see the turbulence intensity value decreases. So in our case, as our height is 100 meters, and we can say that we can assume the value, or we can say terrain category 2 as 0.131. sorry, we do need to take the value at the 50 meters. So at the 50 meter, assuming terrain category 2, the value is 0.151. So we do need to enter the value here is 0.151. The thing that we have considered here is basically 50 meters on terrain category 2. The value here is 0.151. So that has been considered here. After that, the second value that we do need to calculate is the value of the GV. So GV is peak factor for upwind velocity fluctuation, which shall be taken as 3.4. Now in other country codes, there is this formula that is given to calculate the value of the GV. But as per the Australian standard, this value is taken as fixed only. So we can take it as GV as 3.4. So it is irrespective of height, irrespective of terrain categories. This value is fixed. That is GV shall be taken as 3.4. After that, average breadth of the structure between S and H, and average breadth of the structure between height 0 and H. Now we can say that BSH and B0H. So to understand the definition of BSH and B0H, we do need to understand that right now we are talking about the along wind response. So along wind response is that, if you're talking about the breadth of the structure, it means that if the wind is flowing across this direction, we do need to understand that this width plays a very important role. And most of the times it do happens that, let us say, the elevation of the building is something like this. So we can say that, let us assume if we are talking about this particular level, so this is S and this is H and this is 0 level. So the average, if we're talking about two terms here, one is the term BSH. BSH is the average breadth of the structure between height S and H. So average breadth of the structure between this height and this height. So let us assume it as 20 meters. Let us assume. And the second value is basically B0H. So B0H is basically the average breadth of the structure between height 0 and H. It means the average breadth between this height and this height. So let us assume the building is straight. So in that particular case, we can simply take it as B0H also as 20 meter. So that we have considered here, that we have calculated BSH and B0H as per that assumption, and took it as 20 meters. After that, LH is basically the measure of integral turbulence length scale at height H in meter. So in our case, the height H is basically 100 meters. So we can simply use the equation, that is 85 multiplied with 100 to the divided by 10 to the power 0.25. So this number comes out to be 151.15. And after that, height factor for resonant response, that is HS. Height factor for resonant response is basically 1 plus S to the power S divided by S to the square. So 50 divided by 100, and that needs to be squared, and 1 needs to be added on that. So the value comes out to be 1.25. Let me just write the equation also. 1 plus, we can say, 50 divided by 100 to the power square. So this value comes out to be 1.25. And after that, if we are talking about this particular value, the LH, this is nothing but 85 into 100 divided by 10 to the power 0.25. And this we have already understood. BSH and B0H. GV's, the value is fixed. And after that, if we are talking about this value, that is height factor for the resonant response, this is nothing but 1.2 plus 2 log base E multiplied with 600 into NA. Now you need to understand here that NA here is the frequency, the first mode natural frequency vibration in the long wind direction. So as per that, we can simply calculate the value of the NA here. Put in the value of the NA here, and according to that we can find out the value of the height factor for the resonant response. So 600 multiplied with 0.7, and this whole number needs to be taken as under root. So this value comes out to be 3.64. After that, the major equation, that is the size reduction factor. So size reduction factor is basically given as, we can say, so it is given as basically this particular equation, where we have to find out, or we can say understand the meaning of all of these symbols here. Na, we know that 1 plus 3.5. Na is nothing but first mode natural frequency taken as 0.7. H is basically the height of the structure, and height of the structure we know that has been taken as we can say 100 meter multiplied with 1 plus gv that we have already calculated above, and ih also we have calculated. So gv here is basically this particular value, that is 3.4, and ih that also we have calculated, that is 0.151. So we can take it as 3.4 into 0.151 divided with the V design theta. So V design theta that we have already considered as 60 meter per second. So this is the, we can say, first term of the calculation size reduction factor. Similarly, we can take the other value also. The Na is again the first mode natural frequency. B0h is the average width between the 0 and h. Gv is again that we have calculated here, that is 3.4. IH is again turbulence intensity length, that is 0.151 divided with the V design theta. So as per that, we can simply calculate this value as 0.127. So that is the the first, we can say, a typical equation that is given to calculate the size reduction factor. After that, reduced frequency N, that is basically Na into LH 1 plus Gv into IH divided by V design theta. So we can say that this equation is nothing but this equation here. Instead of Na is not written here, and instead of H here, this is LH. So as per that, again we can calculate this value as 2.669. So after that, we can calculate the value of the ET. So ET here is basically pi by 4 times the spectrum of turbulence in the approaching wind stream given by this particular equation. So we can simply calculate that. That is pi into, we can say, N. And here is the reduced frequency, and that divided by 1 plus 70.8 into again N to the power square with the power of 5 by 6. So that gives us the value of ET as 0.047. Now the next thing that we need to put is that we do need to calculate or put the value of the structural damping to the critical damping of the structure. So this is basically the ratio here. So the ratio that we are assuming here is assuming it is a reinforced concrete structure, we can put it as 0.02 here. So after that, background factor. Now background factor, this is quite easy also, we can say. It is a simple equation, 1 plus 0.26 H minus S. So S in our case has been assumed as 0, and 0.46 BSH, that is breadth of the structure between height S and H, divided with LH. LH that we have already calculated above as, this measure of integral turbulence length scale at height S and H. So it is 151.15 meter. So putting the values in this particular equation, we can simply calculate the background factor as 0.84. After that, the major equation comes where we have to put all of these values that we have calculated above. 1 plus 2 IH. So 1 plus 2 IH. IH we have already calculated above as 0.151. Square root, we can say GV square into BS. GV value here is 3.4, and we can say the value of the BS here is 0.84. So 3.4 square into 0.84. Plus we can put the value of HS also. So HS also we have calculated HS, GR, SN, ET. HS value that also we have calculated. HS is this particular value, GR is this particular value, and S and ET. ET is this particular value, and S is this particular value. So we can put all of these values here, and then divide it with the ratio of the critical damping to the ratio structural damping to the critical damping, that we have assumed it as 0.02. So after that, we can again divide this whole value with 1 plus 2 into GV into IH. So GV, that also we can calculate here. So GV also that we have calculated above, and IH that also we have calculated above. So as per that, the value of the Cdyn comes out to be 1.06 at the base level. Similarly, let us just try to change the values here. So let us assume if we are having the same structure, let us say in the steel, so we can put the value of the damping here as 0.015. So the this value become, instead of 1.06, now this value of the Cdyn increases to 1.09. So we can say that steel structures are a little bit more sensitive to wind as compared to the concrete structures. After that, we can change other parameters also. So let us assume the frequency of the building that we are having is, let us say, 0.9. So for 0.9, we are having the value of the Cdyn here as 1.05. And if we were having the value here as 0.7, we were having the value here as 1.09. So obviously, as we decrease the frequency, we increase the time period, or we can say that our the building is getting taller. So let us assuming we are giving here a 0.5 hertz. So we are making the structure more wind sensitive, and with that our value of Cdyn suddenly increases, that is 1.15. Or in the second case, we can assume that the building is getting taller, so we can keep it here as 200 meters. Yeah, and one more thing, let us assume that we have to calculate the value of the at the base itself. So S we can take it as 0 and H we can take it as 100. So the value of Cdyn becomes the maximum, that is 1.1. Similarly, if we are putting the value here as 100, we are getting the value as 1.26. That is the maximum value. That is, we are getting the the value of the Cdyn at the top level. So that is how we can calculate with the different values of S and H, and we can just I shall request you to just change these parameters and try to understand, and if possible do the hand calculation for all of these values, and only after then you should be confident in taking the or doing the practical design of the structures. So I hope we have understood that how we can calculate the value of the Cdyn for calculation of the along wind response for tall buildings and towers. In the next lecture, we shall be discussing about the towers and the horizontal slender structures.